Thank you. Can you hear me? Um, yeah, I hope I do a good job stepping in for Ingo, who unfortunately cannot be here today. Yeah, this talk is going to be about data parallel path tracing. Let me first give you a brief overview of what we're gonna talk about. We're gonna talk about data parallel path tracing, and in particular multi-GPU path tracing. We're going to talk a little bit about what the status quo in this regard currently is versus what we really want, how we really want to do this. I'll explain this method called that we adopt RayQ cycling. I'll present the basic idea. Then have a little time to explain some of the optimizations that we applied. Then I'll wrap it up for showing some results and so on. Yeah, and the talks yesterday, and some of the talks we already heard what the data looks like nowadays. Like we learned that data has become much larger. And this is to do with several factors, for example, with tooling. So for artists and for efforts, it's much simpler to create something small and then replicate it a bunch of times so that you have something really big. And there are other factors that also facilitate this, like, for example, the fact that many rendering pipelines nowadays are based on ray tracing, where the where the complexity is no longer bound by the geometry or is logarithmically bound with the geometry. So that means adding twice as much geometry doesn't make you twice as slow. So that means that big scenes are nowadays even commonplace in games. Yeah, let's talk a little bit about, now that we know what the data looks like, let's talk a little bit about what the hardware looks like when you're not particularly in games, but when you're, for example, in production or when you're doing large-scale scientific visualization. Hardware that you might resort to might, for example, be multi-GPU servers, for example, in the Amazon cloud, or on a supercomputer. And the kind of hardware that we see a lot nowadays are multi-GPU systems, where the multi-GPUs are connected, usually using PCI Express, but quite often actually using some vendor-specific interconnects such as NVLink, which has like extremely high bandwidth. So, and these multi-GPU systems, for example, when you take like a typical cloud-based system and you do the math, you will find that memory actually compounds a lot. You can easily, like on a single system, have hundreds of gigabytes of memory available. So yeah, when you look at the data, I said the data is relatively big usually, but to really saturate these 100 gigabytes of your single multi-GPU system, you need like really big data. And yeah, when you resort to like those hero data sets from NASA, for example, who have their NASA Mars lander data, they're really huge and they might exceed that. But models of the size of hundreds of gigabytes are actually not that easy to get a hold of. So in terms of what we want to use those systems. We want to use them well. We want to use GPUs, obviously, because they have hardware ray tracing. And even if we don't have hardware ray tracing, because we're in an architecture that is more optimized, for example, towards neural nets or something like that, we still want to use optics because we don't want to go through all the hoops implementing BVH intersections and stuff like that. But what we also want is, we want to take that single system and want to ideally use it as though it was a single GPU. And if you take a look at the state of the art in data parallel rendering, for example, Ingo's paper from last year's HPG, you will find that they have like very sophisticated partitioning algorithms that spatially or using BVHs partition the data and then distribute them to multiple nodes, and then quite often use MPI, which adds extra layers of complexity. And we actually don't want all this. What we really want is we want to use the system as though it was a single GPU or a single system. And therefore, we came up with this idea that we called RayQ cycling. And the idea is really simple. What we came up with is, what if we take the data and just think triangle soup, and then chop the data into pieces so that we use as few GPUs as possible, and then generate rays on each GPU, cycle those rays through that in the end, every GPU has traced every ray, and then return it to the GPU that is responsible for shading, and then perform shading there. So this is obviously correct, like when the data is distributed among the GPUs, and every GPU has processed all the rays, and we updated hit records accordingly, then in the end, we'll have something valid, and we'll be like back on the GPU we started at. we can perform shading there. But it's obviously slow, right? Because sending rays over and over consumes a lot of bandwidth. And this is the question that we asked ourselves. Is it really? Or is it not? Let's talk a little bit more detail how we implemented this. So disclaimer, we implemented this actually to find out how slow it really is. And this is what we did. We took the data, and I'll talk a little bit more about data distribution in a little bit, and try to pack it on as few GPUs as possible. Yeah. And then we have a working set of n GPUs that have data in memory, and then we have on each GPU we generate 1/n of the primary rays. So and then we trace on each GPU we trace those primary rays, record the hit information, and store the hit records along with the rays. And when all the GPUs are finished, we take the rays, including hit records, and cycle to the next GPU. Yeah? GPU 0 passes its rays and hit records to GPU 1, GPU 1 to 2, and we make this form a ring. Yeah? And then we cycle n times, and then we are back at the GPU where the cycle started. And then each GPU has traced all the rays, and the information which objects were hit is back at the GPU that dispatched these rays, and then we perform shading. So if we have like a path tracer or something that like that, we repeat that multiple times, like for each bounce that we have. And then in the end, we have a distributed results, like an sRGB result, and that we send back to GPU 0 or whichever GPU is responsible for displaying the image. So that's the idea. It's as simple as it gets. Let's talk a little bit about details. The first and probably most important detail is how to partition the data. And this is also what the big advantage of this method is that partitioning is most simple. I earlier said triangle soup. But that's not really what the data looks like. When you take a look at, like, for example, the Moana Island or some data like this, the data looks more like you have meshes, and then each mesh is associated with a material, and it's maybe a texture or maybe multiple textures. And then you have objects that are composed of meshes. Yeah, think, for example, a tree, and the tree is composed of a trunk mesh and of a leaf mesh, and they together form objects. And then you have instances. Yeah? So you have your Moana Island, and you have like a bunch of trees here, and you have a bunch of trees there, and they're all the same tree, but they're multiplied via instancing. So like a traditional object space partitioner, what would it do? They would just maybe place a split plane in the middle, and then take all the instances to the left, put them on GPU 0, and we'll take all the instances on the right, put them on GPU 1. But then the problem is you also have to replicate the object, right? So, that turns out that can go out of hand real quick because, yeah, you have to replicate the objects, and that's not really what you want to do. What's the alternative to this? The alternative to this is that you directly place the objects on each GPU. And as I said, we can partition however we want. The important bit is we cycle all the rays through all the GPUs. And that allows us to put the data wherever we want. So with this degree of freedom, what you really want is you want to distribute the object. And then you put all the instances where the objects are. This, of course, gives you an awful spatial distribution, but it doesn't matter. Like, you trace a ray into that, and you maybe have a BVH with lots of empty space, but it doesn't matter, because tracing rays nowadays is extremely fast. Yeah, and that's the whole point here. How you partition the data doesn't matter. Like, you just put objects where you want to put objects, and you don't have to do any fancy splitting. Yeah, you don't even have to touch individual triangles or do things with sweep planes or stuff like that. You just take the data. Like when it's triangle soup, it's extremely simple, or when you have like structured volumes or something like that, it's extremely simple. But even in this case, where you have this complex data with multiple instances, with meshes and objects, it's still extremely simple. Yeah, there's the first incarnation of what we had. Just did a round-robin assignment. It turns out that can become quite bad, actually, when you have like a bunch of really large objects. Like, think the Moana Island ocean surface, and then you have like maybe 2 ocean surfaces, and then you probably have like 2 GPUs fully occupied, but you want still want to use relatively little GPU if possible. So we came up with something slightly smarter, where we took all the objects, put them in a priority queue, assigned a weight to them depending on how many instances they have, with an estimate what the BVH costs in memory and things like that. But still extremely simple, priority queue based. Priority queue, pull out the biggest object, put it on the GPU that has the most free memory, and that's it. So extremely simple partitioning compared to your standard object, to your standard data parallel renderer from the past. Let's talk a little bit, like a little bit about some details. For example, one question is how do we do the cycling? So how do we communicate the array queues from one GPU to another? There are several alternatives, two that turned out to be fast enough. One that we call the implicit method, one that we call the explicit method. And the implicit method is really just where we use CUDA managed memory and build one large global address space over all GPUs. Then we use CUDA's memory advice feature to tell each GPU and to tell CUDA where the array queues are, so that we basically pin array queue 0 to GPU 0, array queue 1 to GPU 1, and so on. And then when we run our array generation shader, every thread knows exactly where to access the array queue after each cycle. So basically like a global address space. And the alternative to this is explicit CUDA memory copies. Yeah, we tested both of this. It turns out on PCI Express, where you're actually bandwidth limited, much more than on, for example, NVLink. The explicit copies did a little bit better, so we made this our default, also optimizing implicitly for PCI Express a little bit. So that much about how we cycle those array queues. Another question that is important is how we actually perform shading. As I already said, like we have our trace and cycle phases, and when a trace and cycle phase is finished, the GPU that generated the data also has to perform shading. So this is possible because the hit records are stored with the arrays. Like each array has a hit record. But the problem is that a hit record usually, what does a hit record contain? Like primitive IDs, geometry IDs, instance IDs. That is, with the information of the hit record, you have to do like an indirection to another GPU to retrieve the shading information. So we do something else. What we instead do is, I call them fat hit records. I'm not sure if Ingo is good with that. So we basically store all the BRDF coefficients with the hit record, and if information about the differential geometry that we hit, like the surface normal at the position that we hit, the position in space that we hit, and so on. And that means that when the arrays and their hit records return to the GPU that performs shading, all the information is available that is required to perform the shading. We use the principal BRDF, so actually have a bunch of BRDF coefficients. We pack them a little bit by using half floats. I think we pack vectors where possible. Yeah, but it's actually, it turned out not so bad. There are several alternatives to implement this, but this is what we resorted to. So another question is scalability. When we're in a system, we have like say 4 GPUs available, and we have a model that only occupies 2 GPUs. The question is how to scale. Yeah, we want to use those 4 GPUs, and ideally we also want to become faster, obviously, right? So as I already said, we're doing ray tracing. So we're asymptotically bound logarithmically. That means doubling the geometry doesn't make us twice as slow, but that also means adding more GPU doesn't make us proportionally faster. So just taking the data and instead of chopping it into 2 pieces, chopping it into 4, we don't expect that much acceleration, and we don't expect this to scale so well. So what we do instead is we call this island parallelism. When we have 4 GPUs available and the data fits on 2 GPUs, we just replicate the data and put the duplicate, we put the copy on the 2 available GPUs. Still, each GPU creates a quarter of all the arrays. When we then cycle, each GPU still performs the cycle with its array workload with 1/4 of the arrays, but we only have to cycle 2 times because the data is replicated. So yeah, this turns out to scale real well. I also show this in the results in a little bit. And it scales much better than the naive way of splitting the data into smaller pieces. And yeah, this obviously, of course, extends to different numbers of GPUs and to different what we call island sizes. Yeah, like if the data fits onto 1 GPU, 2 GPUs, 3 GPUs, and so on. Yeah, talking results. Let's have a quick look at what we evaluated. And the first thing I want to say is, like we also did an evaluation on the big irons, like the DGX and RTX servers and whatnot. But one important takeaway here is, if you don't have that, and if you don't need that, your renderer is but a simple wavefront path tracer. Yeah. So I think like the implicit method from before, then your shaders will just access in a global address space, but will access addresses that are on the GPU that we're on. Or CUDA mem copies will not happen if there's no other GPU to copy to. So all this vanishes in thin air, and your whole system becomes an ordinary wavefront path tracer. Yeah? This is actually how we use this a lot of the times. So, I mean, for this evaluation, we're really interested in like the big models and the big hardware. So we performed our evaluation on a DGX2 station, which is a Volta architecture-based workstation, which is 16 GPUs, 32 gigabyte each, which is NVLink. That is you have like peer-to-peer communication is on the order of 270 gigabytes. Bandwidth, which is a lot. But we don't have hardware accelerated trace because this is not an RTX GPU. And then we use an RTX server with 8 RTX GPUs, with hardware ray tracing. But as an interconnect only has PCI Express 4.0, which is like roughly an order of magnitude lower on bandwidth. For our test data sets, we used like these data sets that you probably know, like the PBRT landscape scene. I think in 3 different sizes actually, so this slide is missing these. We used 2 different versions of the Moana Island, one smaller, one bigger, where we like replicated some of the textures differently, unrolled some of the subdivision surfaces and so on. And then we also have like a large indoor scene that is bigger than 100 gigabytes in size. And then we performed several tests, but particularly we also performed a scalability test because we're interested in the scalability of our system, where we implemented a simple path tracer on top of our framework, nothing fancy, uses a bit of next event estimation, I think reservoir sampling for some area lights, environment lighting, diffuse BRDFs mostly, and some specular BRDFs for water surfaces, like think the Moana Island or the landscape where there's like water in there. And then we evaluated this, and these are our results for this. On the left side is the RTX server, and the right side is the DGX server. And there's several takeaways here. The first thing to note is that whenever there is a dot in one of those graphs, that means we create another island. Like those 2. It's probably not possible for me to, but those 2 blue polylines up there are models that fit within 1 GPU. Like whenever there is a dot, we make the decision, use another GPU, create another island, duplicate the data, duplicate the data. And the green line, the dark green line, for example, is a model that fits onto 2 GPUs. So we see extremely well scalability here in terms of this kind of parallelism. And there's also other things that we can see. We can, for example, see that on the RTX server, we are generally faster because we are bound by trace. We can also see that the polylines, when the data gets distributed on the RTX server, which has PCI Express, are all below the 1 GPU lines. That means here bandwidth matters. We can see how the polylines for the models that are distributed among multiple GPUs move closer to the polylines for the 1 GPU model on the DGX, which also makes sense because we have a whole lot more bandwidth. And here we are more bound by trace. Here, there's a lot of things to read from these graphs. For comparison, these here are the graphs for the method without islands. Yeah? Scalability with the naive method from before, where you take the data, and if you have 4 GPUs, make 4 smaller pieces. And you can see that for most of the data, we see diminishing returns, if not even negative. Yeah, that already brings me to the conclusion of my talk. I presented what we think is a extremely simple method. We just distributed the data just as it comes, and then we trace a whole bunch of arrays and wait for them to finish, and then repeat this over and over. So it's extremely simple, and the amazing thing, it's fast. Like I couldn't go into the details here in this talk, but we also beat several of our competitors in terms of frame rates. But the really amazing thing is really how simple this method is. Yeah, from an engineering point of view, and with the very little processing time that is available, that is necessary, and with the engineering constants that are really low compared to your typical data parallel path tracer with all the bells and whistles and complicated splitters and partitioners and so on. Yeah, this is the end of my talk, and I'm now happy to take questions.
Thank you very much for the nice talk. Any questions? Ooh, all the way in the back. I'm going to try.
This is also multiple hop. We have to cycle it through.
So the other sort of like non-trivially large data can be texture. And what if the textures don't fit? Like you didn't really talk about how textures would be distributed or how work would be assigned if textures are on different nodes.
Yeah, this is a good question. It kind of like depends. Yeah, this is a very good question. Like if the textures exceed the memory, I think this is supported. I think that we actually support this because then we can just split the data more. Yes, our partitioning scheme, say weight estimate for the object. So if there's one large object where the textures exceed the GPU memory, then we have some problems. But if not, if like the overall texture memory gets exceeded, then we just split the data more. We just split the data more. We have a weight estimate, and based on the weight estimate, we just use more GPUs. I hope this answers the question. I mean,
partly, yeah. I'm just wondering how the work gets assigned. Because it's not just shuttled necessarily to the next GPU.
Yeah, during the work assignment, we take the texture overhead into account. We compute how much texture we use on the respective GPUs, and we take this into account. Yes.
Okay. I'll ask you later.
Any other questions?
Very nice talk, Stefan. So I'm wondering, do you have a graph where you kind of disable where you have PCI config but disable the ray tracing hardware, just to see the impact on this?
Yeah, this would be interesting. We're on optics, and you cannot. So like there's RTX on, RTX off, and in reality this does not exist. So you cannot just tell it don't use the software BVH. We had a software BVH, but for other reasons, because the reason being that we also tested with striping the BVH and not just the data. So I remember that this in particular was quite slow, but I'm not sure if there's like a certain implementation constants that adds to that. So the question is really like, how would like a really well-engineered BVH like the one in RTX, but software perform? I don't know this. I can deduce a little bit from the graphs that I showed earlier that on the Volta systems we're really limited by trace, so that's indicative of that this is an issue. But I cannot really tell. But there's no like magic switch in reality where you can say RTX on, RTX off. Unfortunately.
Okay, thank you.
One question over there. All the way on the left. Yes.
Excellent presentation, thanks. How do you handle shaders that require actual intersection without being able to exit the shader? For example, rounded corners, ambient occlusion, and how do you handle different ray types? For example, you spawn those shadow rays. You mentioned it's a wavefront approach. It's not like tracing the entire path and then returning to the same entry point. So this is something that confuses me, and I need a little more explanation.
Yeah, this sounds more like a general wavefront ray tracing question, right? So the question is, what happens if you have like a ray tree and not a ray list, right? With shadow rays, there's this trick where you take the radiance that you computed with the first ray and then carry it along, compute a shadow ray, and then you still have the radiance, trace the shadow ray, and then you decide if there's occlusion or if the radiance carries through to the intersection. And that allows you to build a list of rays, one for visibility, one for shading, one for shadow, and then like you concatenate these. So, and this in reality, this is what we do in our wavefront ray tracer. Yeah, and for path tracing, which is like a depth search, this is perfectly fine. Like the case where the rays really branch out, our framework does not support this. I haven't thought much about this, how to support this. I'm not sure if it's possible. But for a path tracer, where it's either a depth search through the path space, or you can reformulate the problem to a depth search through the path space. I think this is not an issue. At least this is what I'd say.
Okay, thank you, Stefan.
Yes.
Considering the time, save the remaining questions for the coffee break. And let's thank our speaker once more, Stefan.